the types of errors that we have that we need to be able to deal with in higher physics to percentage errors, which really apply when we are doing calculations. So if you've got a circuit like so, we've got a circuit there, and if we want to calculate power, we can get voltage from here, we can get current from here, and we can use P equals IV. So we had two readings that we took from analog meters. Remember, analog meters, the reading error on an analog meter is plus or minus half a scale division. So we've got 8.5 volts for the voltage, and we've got 1.6, is that, I think, for the current. We take those two values, but they're both prone to error. They've both got some kind of uncertainty there because, you know, there's a measurement involved in that. There's some sort of reading involved on the scale. So we need to figure out in any calculation which one has the largest percentage error, and that's the one that we will use in the final answer. Before now, we've only had one type of error, so we haven't had to figure out what the total final error was. But now we do. Now we have, you know, we're trying to calculate power and we're trying to calculate what the error in power is, but we've got two different uncertainties there. We've got an uncertainty in the current and an uncertainty in the voltage. So the one that we use is the one that is the largest percentage. So we can calculate percentage error by using this formula here. So it really is just a basic percentage. It's the error divided by the value times 100. So it tells you what percentage of the overall value the error is. So we calculate P equals IV first, and you get 13.6. That's your final value. So whereas when we've got multiple values, we calculate what the mean is, and that's what our final answer becomes. Here, we don't have multiple measurements. We've only got one, or it's one set of measurements. So 13.6 is our answer there. We then need to go on and calculate what the error is in V and what the error is in I. So the error in V here is 8.5. 8.5 is the reading, and half a scale division is 0.05. So that's our error there. So we do that, calculate a percentage. Do the same for I. Half a scale division is 0.1. Divide that by 1.6. We've got a much larger percentage error in the current reading because it's got a smaller scale, a much smaller scale. 6.25% then becomes the percentage error that we use in our final answer. So 13.6 watts plus or minus 6.25%. So that would be us expressing that answer in percentage form. We can also present it in something called absolute form, which is really the numerical form rather than the percentage. So we then use that, we calculate what 6.25% of 13.6 watts is, and we find it's 0.85. But as a final answer, we express them in the same number of significant figures, so we use 0.9. So absolute and percentage formats. Percentage format, you express your uncertainty plus or minus some percentage value. Absolute is plus or minus a number, so it's a number as opposed to the percentage. After that, we did a quick experiment just to show you, you know, that these types of errors are real and, you know, they do happen in everyday experiments. So measuring room temperature with an analog and a digital thermometer, we found that, you know, they both read about the same value, but the error within them is different. The error in the analog scale is greater because that's plus or minus half a scale division, whereas it's plus or minus 1 in the least significant digit for a digital scale. So it has a larger percentage error, therefore it's less accurate. So there's more room for error within that. So percentage errors, it's really just taking the error, dividing it by the value, multiplying by 100, and also know the difference between absolute and percentage errors. Absolute errors is a number, percentage errors is plus or minus a percentage.